Hey everybody, it's Mr. Molecash again, and I was going to follow up that last video about improper integrals to do some more examples. So we'll call this improper integrals part 2. And just wanted to follow up with you and remember that you can use lots of techniques to find an antiderivative, U substitution being one of them. Here's a problem that I'm copying out of Delta Math, and it says to evaluate this integral or state that the integral diverges. This is straight out of Delta Math. Okay, so right off I can see that I'm going to want to use U substitution because the derivative of 4x to the 5th is 20x to the 4th, and there's a 20x to the 4th right there, right? Okay. So if we let u be 4x to the 5th, then du would be 20x to the 4th dx. And there's lots of different ways that we can approach this. For example, this is 2 times 20. So I can sort of make this fit. I'm not exactly sure how Mr. Abdel does these integrals, but I can sort of make the pattern fit, right? I can make it fit. So the first thing I'm going to do is rewrite that negative 40 as negative 2 times 20x to the 4th. And I can separate the negative 2 right there. And the reason I'm doing that is because this part and this part is precisely du, right? And then this is just e to the u. So that's a pretty easy antiderivative to do. The problem is I've forgotten about the limits here. Let me go ahead and color those limits in. And it's important to know that you can just keep everything in terms of u here. Erase that u and make it look a little bit better. Oops. There we go. U. All right. Hopefully it looks a little bit more like a u. So over here, I'm going to change the limits from x limits to u limits, right? So when x is approaching negative infinity, what's happening with u? Well, in the letter u, not y-o-u. Anyway, it should be clear by looking at this that when x is negative infinity, or when x is approaching negative infinity, the u is approaching negative infinity even faster, right? So we're still going to have our negative infinity there. But when x is equal to negative 1, we can plug in our x equals negative 1 into this expression to find out what u is. And that's going to be negative 4, right? Okay, so we'll have an integral where u is approaching negative infinity and u is equal to negative 4 because our variable of integration is u. Okay, so I've decided to change the limits from x limits to u limits. Okay, furthermore, it's easy to find the antiderivative, right? So that's going to be e to the u. But what we're going to have to do here, let me move that over a little bit. What we're going to have to do here is calculate the limit as b approaches negative infinity of this expression evaluated from b to negative 4. Okay, and so we get the limit as all this is multiplied by negative 2. So this should be e to the negative 4 minus what? Well, it should be clear that the limit as b approaches negative infinity of this is 0, right? Because they're exponential function. As you go off to the left, you're using a horizontal asymptote of y equals 0, right? Okay, so that pretty much gives us our answer, right? So what we're going to have to do now is, let me see if I can just fit this in here. Maybe I can fit it in this lower right-hand corner. This is going to be negative 2 times e to the negative 4th minus 0, which should be negative 2 e to the negative 4. And off screen here, I'm just going to go ahead and type that in and see if that works in my Delta Math application here. So it's a negative 2 e to the negative 4. And I'm going to hit submit answer. And I get a green check mark. Okay. Now, it's important to know that when Delta Math is doing this problem, that they keep their limits in terms of u as well, right? So that's the reason why I decided to do it this way. Okay, all right, let's do another one just so you can see, you know, another kind of example with improper integrals. And let's see, this time I'll just use blue. So this one is going to be the integral from 1 to infinity of x e to the negative x dx. And you might remember that huge shortcut in doing the antiderivative here is the tabular use of integration by parts, right? And we're going to let u be this x, right? So that's pretty easy to keep differentiating. The dv is going to be our e to the negative x. Technically, there's a dx there. We won't write it in this table. And every time we integrate e to the negative x, we get the opposite of e to the negative x. So that's going to change sign every time due to the exponent, right? And so it's easy to connect this. So antiderivative is going to be that connection minus this connection. Okay, so there's our antiderivative. And then, of course, we're going to have to evaluate this from 1 to b, where we're taking the limit as b approaches infinity. And so it might be helpful to rewrite this antiderivative with positive exponents, right? So we'll have negative x over e to the x minus 1 over e to the x from 1 to b. And if we do, sorry that happened there, if we do the b term first, or the b limit first, okay, and then we subtract from that what happens when we get 1 in there, so that's negative 1 over e minus 1 over e. It should be pretty clear that as b approaches infinity, the top of this fraction is going to grow way slower than the bottom, right? Way slower. So the limit of both of these expressions when b is approaching infinity is 0. So we're going to have 0 minus 0, subtract, and then combining terms here, we get negative 2 over e. So that should be positive 2 over e. Okay, and of course you can try to verify this with your Decimus calculator like I showed in the last video. Of course, Delta Math has problems where you're doing the graphical representation of an improper integral as well. Okay, so reach out to me if you need help. I'm here to help. I appreciate you guys hanging in there. Until next time.